section 1.8, which is a bit strange for a couple reasons. One reason is because we're skipping 1.6 and 1.7. The reason for that is both those sections have to do with infinite sequences and series, and if you remember, you did that in pre-calculus 11, so I don't see the need to do that here. And second reason it's a bit strange is that this video is titled Review. I don't often make videos for the review. In fact, what I've done here is I've collected a few things that I kind of glossed over or skipped completely in chapter 1, and I want to introduce them to you in here. I think if I was to skip them completely, there might be a time next year in calculus at university where you might say, wait a minute, Waj never told us about this, and I would hate for that to happen. So these things are important, and I'm going to introduce them to you now. So the first thing is a whole bunch of properties. I'm going to go through 7 properties of limits. These properties also apply to one-sided limits. So you've kind of used these properties without having ever been explicitly taught them. They're almost common sense. I mean, I think it's a bit strong, but I imagine that when I show you these things, after a couple of them, you're going to be like, oh, okay, I guess that makes sense for the rest of them. So here we go. Let's get right into this. Suppose that the limits the limit of f of x as x approaches a and the limit of g of x as x approaches a both exist, so we don't have to worry about that. And we're also going to let c, anywhere where we see c show up here, like right here, we're going to let c be a constant. So then here's the first property, in no particular order, but here's one property. The limit of f of x plus g of x as x approaches a is equal to the limit of f of x as x approaches a plus the limit of g of x as x approaches a. So you can apply this limit statement individually to each one of these functions here. So I'm going to give you an example of each one of these properties. So for our first example, we're going to have the limit of x plus 5 as x approaches negative 2. Now, what this property is saying is, because we have two terms here, we have the x is one term and the 5 is the other term. This first property tells me that I can consider them separately. I can take the limit of x as x approaches negative 2, and then since I'm adding here, I would also be adding here, I could take the limit of the second term, which is 5, as x approaches negative 2. And then we can just do this individually. So for this first limit, as x approaches negative 2, what does x approach? Well, you just plug negative 2 in there, you get negative 2. For the second one, as x approaches negative 2, what does 5 approach? Well, 5 is 5. No matter what x approaches, the output we're always getting here is 5. So you end up with negative 2 plus 5, which equals 3. There's your answer. Now, I know what you're probably saying is, what was the point of this? Like, why didn't we just substitute in back here? Why wouldn't I have just substituted in negative 2 right here and got a negative 2 plus 5 is positive 3? And the answer is, you would do that. But this property is just showing you that you're allowed to do that because of this reason here, because this property holds. So again, this is why I didn't introduce you to all these properties before. I think they kind of make it more complicated, but this is actually showing you that all the things we've done before, they're actually valid steps. So we say here that the limit of a sum, so here's our sum, and we're taking the limit of it, is the sum of the limits. Yeah? Okay, next one. This time we have the limit of a difference is the difference of the limits. It's almost exactly the same. If you take the limit of f of x minus g of x as x approaches a, it's the same as the limit of f of x as x approaches a, take away the limit of g of x as x approaches a. So here's another example. The limit of x minus 7 as x approaches 10. Well, this property tells us we can again split those two terms up and apply the limit to each one. So we'll have the limit of x as x approaches 10 minus, since it was minus here, it'll be minus here, minus the limit of 7 as x approaches 10. Okay, so now we can evaluate each limit individually. As x approaches 10, x approaches 10. I know that's kind of silly to say that way, but that's what it does. You just plug that 10 into the x, and as x approaches 10, 7 approaches, well, 7 is 7. So we just get 10 minus 7 equals 3. All right, the next one. Remember that c stands for a constant. So what we have here is a constant times a function. And what this property says is if there's a constant there, you're allowed to remove the constant and just take the limit of the function itself and not worry about the constant. So an example of that would be something like the limit of 2 times x minus 1 as x approaches 4 equals. So we have two things here. We have a constant, which is 2, and we have a function, which is x minus 1. And what this property says we can do is actually just move the 2 out front and then take the limit of x minus 1 as x approaches 4. That's very useful. 2 is just 2. We'll just keep it there. Now what we're going to do is evaluate this limit. The limit of x minus 1 as x approaches 4, well, you just substitute the 4 in there and you end up getting 3. 4 minus 1 is 3, and then 2 times 3 is 6. By the way, when we evaluated this limit, which property did we have to use to evaluate that limit? We used the difference property, this one right here. The limit of a difference is the difference of limits. We have two things here which we're subtracting, and this property tells us we can just plug right in there. Okay, number 4. This time we're multiplying two functions together. So the limit of f of x times g of x as x approaches a is the limit of f of x as x approaches a times the limit of g of x as x approaches a. So the limit of a product is the product of limits. Example, let's say we were doing something like the limit of 3x as x approaches negative 5. So I'm keeping things very simple here, right? My two functions, the first function is just 3, I mean it's a bit basic, and the second function is x. And what this property tells us is we can take the limit of 3 as x approaches negative 5 and multiply it by the limit of x as x approaches negative 5. So as x approaches negative 5, 3 is just 3. Nothing happens there. As x approaches negative 5, x is negative 5. Just substitute in. So you get 3 times negative 5, which is negative 15. Okay, very similar to that one. This time we have the limit of a quotient is the quotient of the limits. So we take the limit of two functions that you're dividing. You can take the limit of the numerator and then divide it by the limit of the denominator. Notice, of course, that the limit of the denominator cannot equal 0 because you can never divide by 0. So here's our example of this one. Let's do the limit of 3 minus x divided by x as x approaches 3. So what this property is telling us is that we can take the limit of 3 minus x as x approaches 3 and divide it by the limit of x as x approaches 3. Okay, now you can just evaluate both of these limits. Of course, you'd be using, again, property number 2 here, but you know, once we've gone over these properties, you don't have to always explicitly mention them or anything. That's why the properties are useful, to simplify things for you. So on the top, we'd be putting 3 minus 3 in there, so you'd get 0. And the bottom, you'd be substituting in just 3, so you get 0 over 3. That's fine. 0 over 3 is 0. Number 6, I haven't left myself much space here. This is the limit of a power is the power of the limit. So what's that saying? It's saying if you take the limit of f of x raised to the nth power as x approaches a, it's the same as limit of f of x as x approaches a raised to the nth power. So an example is, nice color here, the limit of x plus 3 all squared as x approaches 2. And what this limit tells us is that we can actually save the squaring to the end. We can take the limit of x plus 3 as x approaches 2, and then once we have that, we can square it. So that's nice. That means we don't have to expand all this and everything, right? We can easily evaluate this limit. Just plug 2 into here. You get 2 plus 3 is 5, and then we square it, and we get 25. And the last one, the limit of a root is the root of the limit, if the root exists. So this is saying that the limit of the nth root of f of x as x approaches a is equal to the nth root of the limit of f of x as x approaches a. It's getting a little bit complicated, isn't it? But the property itself isn't all that complicated. So an example will make it clear to you. If we ask for the limit of the square root of 2x minus 1 as x approaches 5, what we can actually do is take the square root of the whole thing and say the square root of the limit of 2x minus 1 as x approaches 5. So so we can save the square root to the end. We're going to evaluate the limit inside by plugging 5 in here. So 2 times 5 is 10, take away 1 is 9. I think my square root sign is a little bit big here, so we just need to take the square root of that, and the square root of 9 is 3. So there you go, 7 properties. As I said, it's not like you have to think about them all the time, but just be thankful you don't have to think about them all the time, because these properties are, assuring us, if you want, that we can do all these steps that I've shown you here. Okay, the next thing I want to talk about are discontinuities. We did talk about discontinuities before, and we talked about them when we were talking about functions being continuous. And when we talked about functions being continuous, we said there was 3 situations that need to be met, that need to be true. So there were these 3 things right here. And maybe just to quickly go over this again, I will sketch a little function for us. Here's our function right here. And one thing that we said had to be true in order for a function to be continuous is that f of a exists. So let's consider the point 4. So in order for this to be continuous at that point 4, where our a value is 4, f of 4 would need to exist. Does it? Sure does, because there's a point right there. Which point is it? I don't know. Let's just say it's 6. I don't know for sure it actually is, but let's just say it's 6. Okay, so that would be met. Good. The next thing would need to be true is that the limit of f of x as x approaches a, or in other words, as x approaches 4 in this case, needs to exist. So how would we know? How would we know whether the limit of f of x as x approaches 4, whether it exists or not? Well, what we'd do is we'd first of all look from each side. We'd look from the left-hand side of 4. Okay, so I'm just going to put a point there. And as we look at this function from the left, getting closer and closer to an x value of 4, you can see that we're getting very, very close to a y value of 6. Okay, so from our left-sided limit would be 6 would be the answer. Then we would look from the right-hand side. And as we look closer and closer to an x value of 4 from this side, our y value again is getting really, really close to 6. So because the left-hand limit and the right-hand limit equal the same thing, we can actually say the limit exists, and it is 6 as well. Okay, so this one's good. Third thing that needs to be true is that the limit of f of x as x approaches a, well that's this right here where we got 6, needs to equal f of a. Well that's this where we also got 6. So yeah, it worked. We need this number and this number to be the same, and they are. So this is continuous function right there. But for example, if we had an open circle right here, if it wasn't closed but was open, then this would not exist. How come? Because it would fail the very first step here. This f of 4, what's f of 4 if this is an open circle? F of 4 doesn't exist. There's no point there. So we would not have a continuous function at that point. In fact, there's 3 types of discontinuities, and what I just mentioned with the open circle is the first type, which is removable discontinuity. So with a removable discontinuity, it's characterized by the fact that the limit exists. The limit does exist, even if we have this open circle here. In this case right here, the limit does exist. Because if I look from the left-hand side, as I get closer and closer to 4, it's approaching 6. As I look from the right-hand side, and I get closer and closer to 4, it's approaching 6. So yeah, the limit exists. It's 6, but f of 4 does not exist. So because of that, it's discontinuous. Okay? A hole shows up in the function. So that's this example right here, where you get a hole in the function. Next type of discontinuity is a jump discontinuity, and that is when both one-sided limits exist but have different values. So what that would look like, I mean, it's a good name, a jump. That would look something like this. Say this is our function, and it goes like this, and then it goes like that. Looks like a couple sperms swimming along here, but that's not what I'm trying to draw. So if we look from, let's say this point here is 4 again. If we look at our left-handed limit here as x approaches 4, then what value would it be? From the left-hand side, it's approaching this value right here. Let's say that that's 2. So we would say that the limit as x approaches 4 from the left of this function, it looks like it's going towards 2. But if you look at this function, the limit of f as x approaches 4 from the right, it does not look like it's approaching 2. It looks like it's approaching, let's say this is 1 here, right? As we come closer and closer to 4 from this side, it's getting, the y value is approaching 1. So yes, the left-hand limit exists, and yes, a right-hand side limit a right-hand limit exist, but they're not equal to each other, this is called a jump discontinuity. And it makes sense how it's a jump, right? You're jumping from one to the other. Kind of makes sense that this is removable, because if you removed that circle there and filled it in, I guess, you'd actually would not be discontinuous. Okay, the last one is an infinite discontinuity, and this is also a very good name because this is when both one-side limits are infinite. This should also say one-sided limits are infinite. So an example of that, I suppose, would be something like this. You've got a limit that you've got a function that goes up and up and up and up like this, and it also goes up and up and up like this, and I don't know, continues out this way and it continues out that way, whatever. But the key is that these two here are tending towards an asymptote going up towards infinity, so this is an infinite discontinuity. Both one-sided limits are infinite. It doesn't have to be positive infinity, it could also go down to negative infinity. One or both of them could go down to negative infinity. Alright, so this question here asks, where are the discontinuities in this function? Why is it discontinuous there? And what type of discontinuity is it? So there are 1, 2, 3 discontinuities in this picture. Surprise, surprise, there's one of each type. So let's find the removable discontinuity first. Where's the removable discontinuity? The removable discontinuity is right here. So I'm going to put removable. Do I have to write discontinuity every time? First of all, I hate saying it, and it's a long thing to write too. Discontinuity. So what we want to figure out is why. Why is this a discontinuity? So the first thing we want to see, this is at the point when x is 2. We want to see, does f of 2 exists? And I know you might be tempted to say no here because of the circle, but f of 2 does exist. What's f of 2? F of 2 is -1, this dot here. This dot has an x value of 2, which is what we're interested in, and a y value of -1. So this actually passes our first criteria here. F of 2 needs to exist, and it does. But I think you can probably already see what the problem is. The next thing you have to do is you're going to have to look at the limits. So the left-hand and right-hand limits. So the limit as x approaches 2 from the left-hand side of this function is equal to what? Okay, as we approach 2 from this side, boy, it's getting very, very close to -0.5. How about the limit of f of x as we approach 2 from the right-hand side? Okay, we're getting closer and closer to 2. It looks like our y value, again, is getting close to -0.5. So those are equal to each other. Left and right-hand side are the same, which means the limit of f of x as x approaches 2 is equal to -0.5. So the second criteria is also good. The limit f of x as x approaches 2 exists. So what's the problem here? The problem is the third criteria here. What needs to be true is that -1, the answer we got here, has to be equal to this number here, and it's not. So this is a removable discontinuity. I don't know if it's going to help you or confuse you, but you could put something like -1 does not equal -0.5. I don't know, but the key is these two things must be the same as each other. All right, let's go to the jump discontinuity. Which one's the jump discontinuity? This one here, when x equals -3, we're jumping way up here, we're jumping way down there. So again, let's go through our steps here. All right, let's name this first. This is our jump discontinuity. And let's go through our steps here. So the first criteria is that f of, in this case, -3 has to exist. Does it exist? Yep, it does exist, because at -3 there is one point on this function that has an x value of -3. Which point is it? This point right here. Looks like, I don't know, 0.7 or something. Sorry, it's not clear, but I'll put 0.7. So first criteria, good. Next thing we have to do, we have to figure out the one-sided limits. So the limit of f of x as x approaches -3 from the left. Well, as we go from the left, it's getting very, very close to a y value of, what's that, about -0.9? -0.9. As we look from the right, the limit of f of x as x approaches -3 from the right. So we're getting really, really close to negative 3 on the right, and we're getting close to a y value of 0.7. So on one side we got negative 0.9, on the other side we got 0.7. So what does that mean about the limit of this function overall as x approaches negative 3? It means it does not exist, right? Those two numbers have to be the same for the limit to exist. So this does not exist, which means it fails this second criteria right there. Okay, the last one is where? Right here. We have an infinite discontinuity there. So let's write that in. Infinite discontinuity. Gosh, that's a pain to write. All right, so it's when x equals negative 1. So let's go through our steps again. And we need to see whether f of negative 1 exists. So does f of negative 1 exist? No, it doesn't. So we already know we're done. It does not exist there. F of negative 1, there's no point there. Let's just go on though. I just want to make a point here. Let's take the limits of both sides. So we have the limit of f of x as x approaches negative 1 from the left. And as we approach it from the left, what are we getting closer and closer to? Well, it's really going up. It's going up towards infinity. Okay, as we look from the right, the limit of f of x as x approaches negative 1 from the right. What does that equal? Okay, getting closer and closer to negative 1 from the right hand side, it's going way up towards infinity. So what does that mean about the limit of f of x as x approaches negative 1? That means since it's infinity here, it's infinity here. Now, I know I've said this before, but I just want to say it again. Does this mean that the limit exists? No, it doesn't. I know we have an answer here, but that's just telling you that the limit does not exist, and it doesn't exist in a special way, and it's this way where it goes towards infinity. So the first criteria was that f of, in this case, what number are we looking at? Negative 1. F of negative 1 exists? Nope. The second one is that the limit of f of x as x approaches negative 1 exists, and that's again a nope. So for two reasons, and the third one will be also a nope, of course, this one definitely does not, is not continuous. So there's your three types of discontinuities. Okay, this is the end of chapter 1. For many people, they find this the most confusing one to contextualize. I'm not saying the course gets easier now, but I'm saying that there's a lot of things in this chapter that were difficult to picture or to wrap your head around. After this, a lot of the difficulty has to do with like complicated algebra and stuff, but it's easier to understand what we're actually doing. Okay, good work everyone. Take care.